Ever wondered how we describe the orientation of an object in 3D space? How would we define the rotation of this cube from here to here? One common way is using Euler angles. Euler angles break down a complex rotation into three simple chained rotations about the axis of the cube to represent any 3D orientation. Let's look at this cube. This cube has three axes, the X, Y, and Z axis. This cube starts out oriented with the world reference frame, X, Y, and Z. To model this rotation, we will follow a ZYX rotation sequence. First, we rotate the cube about the Z-axis by some angle psi. When we do this, notice that the X and Y axes of the cube have been rotated by psi, creating a new local axes X' and Y'. We then move on to our second rotation. This time, we rotate the cube about this new Y' axis by an angle theta. This rotation rotates our Z and X' axes, creating a new Z' and X" axis. Finally, we rotate the cube about the new X" axis by an angle phi. This rotation rotates the Z' and Y' axes to become our new final X', Y', and Z' axes. We now have represented our final orientation by breaking one complex rotation into three simple rotations with three angles. You may have noticed that I chose a specific convention ZYX, representing the order of axes that we rotate about. What if we chose to rotate by X, Y, Z? Well, let's try it. When we do so, we get a completely different orientation. When we define these rotations, order matters. This ZYX convention is especially useful in aerospace because it's so intuitive to understand. Let's swap our cube for an aircraft. This aircraft has a frame with the X-axis out the front, the Y-axis out the right wing, and the Z-axis pointing down. Using our ZYX convention allows us to define the aircraft's attitude with three familiar terms. The first rotation about the Z-axis gives us our heading, or yaw. The second rotation about the new Y-axis gives us our pitch angle. And finally, our third rotation about the newest X-axis yields our roll angle. This direct mapping to yaw, pitch, and roll makes Euler angles perfect for pilot interfaces and high-level descriptions of flight. However, this convenience comes with a severe drawback that we call Gimbal Lock. Here, our cube is mounted in a physical gimbal system representing our three rotation axes. The outer ring is yaw, the middle is pitch, and the inner is roll. Normally, these rings move in this yaw, pitch, roll hierarchy. But watch what happens when we pitch the cube up by 90 degrees. The axis for the outer yaw ring and the axis for the inner roll ring are now pointing in the exact same direction. These gimbals have become aligned. This is Gimbal Lock. When we yaw and when we roll, we perform the same motion. We have lost a degree of freedom. This can cause chaotic, uncontrollable spinning. So, while Euler angles are intuitive and easy to understand, their dependency on convention and issues with Gimbal Lock mean that they are not the best orientation representation in systems. In later videos, we will look at alternative methods to represent orientation.